Hi, everyone. Today I want to go over a problem similar to number 24 in chapter 8, which asks you to, it's a little different than this, but I just created my own version. Similarities are, in both of these problems, we're going to be taking an intersection over just a huge collection of sets. And in both cases, we're going to be dealing with intervals. And in both cases, we want to show this intersection is equal to some very nice interval. So this should help quite a bit with that one homework problem. And the first thing I recommend to do in cases like this is define a shorthand for yourself. So I'm just going to call each of these sets here, each of these intervals, a sub x. Right, so a sub x depends on what value of x you choose, and it just looks like this. And it's super important to remember that each of these is an interval in the real line. Right, it's some actual subset, some actual like dense subset of R. It's not the set containing these two elements. And I know most of the time we deal with sets, so it's easy to not look at the symbols on the outside, but it's actually talking about an interval, right? Every number between these two endpoints. Once you do that, I highly recommend you think of some examples. So like plug in some values for x. Right, this will be where x is 2. Right, so if I plug in 2 for x, just think about what set I get, or what interval I get. That would be 2 minus 2 plus 1. And the right endpoint would be 5 plus the absolute value of 2 plus 1. So that would be, let's say 2 minus 3, that's -1. 5 plus 3 is 8. And similarly, if I choose the value x equals 1, plug 1 in for each of those, let's see what we get. That would just be, maybe I'll just do it in my head really fast. That would be 0 to 7. If I plug 0 in for both, then I would get 1 to 6. And so you kind of start to see a pattern. And if you look at the left endpoints, we get -1, 0, 1. So it seems like it's increasing by 1 each time. Whereas for the right endpoints, you get 8, 7, 6. It looks like it's decreasing by 1. But of course, I don't have to just pick, nice non-negative integers here. I could also, our indexing set is all of the real numbers. Right, so I should think about any real number x, maybe a negative integer would be good. If I plug in x equals -1, that would look like, well, looks like 2 and then 5. Okay, so pattern keeps going, it seems like. If I plug in -2, I get, what do I get? 2 minus -2 plus 1. 5 plus -2 plus 1 in absolute value. And that actually gets kind of interesting, right? Because then this is the first time we see that the thing inside the absolute value is negative. Right? So -2 plus 1 is -1. In absolute value, that's 1. So then 2 minus 1 is 1. And then if I evaluate this, I get 6. So actually the pattern doesn't continue forever. In fact, you get a nice pairing. A -2 is the same as a 0. And if you went one further, a -3 would be exactly the same as A1. So the pattern seems to be that for a large positive value of x, we get some large open interval, which then steadily decreases, but then kind of rebounds and gets larger again. If you wanted to draw it on a number line, which I do recommend doing, it's actually a very good strategy. I guess I only have to go up to 8, I think. So drawing these on the number line, well, A2 was the interval from -1 to 8. So we have this open interval, is A2. A1 was 0 to 7. A1 was 0 to 7. And then 1 to 6 and 2 to 5. But then 2 to 5 is where it actually rebounds. Right, so it shrinks and then it bounces back out. So, and once you think about it like that, going back to the statement of the theorem, hopefully it's a little more intuitive. You're saying that the intersection of all these sets A sub x is actually equal to the interval 2 to 5. Well, that's because when I take the intersection of all these things I drew down here, you can sort of think of it as just producing the smallest one. Right? It started out big, compressed until you hit 2.5, and then bounced off. So hopefully it's clear why the interval from 2 to 5 is in fact the intersection. It's sort of the smallest one. All right, but of course that's not a proof. So how would we prove this? So let's start from scratch. Let me just write down AX again. AX is the open interval from 2 minus the absolute value of x plus 1 to 5 plus that absolute value. And our goal is going to be to show two things. We want to show that the intersection is equal to the open interval from 2 to 5. But that means we really want to show, first, it's a subset in this direction. Second, it's a subset in the other direction. So 2, 5 is a subset of the intersection of all these intervals. If we're able to do that, subset in one direction and subset in the other, we've showed equality. So let's write out our proof. Let's start with this direction. I'll just sketch some of the basic ideas. As always, we want to start with an element on the left. So I'll say let, I'd like to use x, but x is already used, so let's use y. So we'll say y is in the intersection of all the ax's. Right, and I really want to stress here, by the way, again, that this intersection is over all real numbers. So even though I only did some nice examples where I was using integers for x, I could have written down like a half or a sub pi or something weird. Right, so you're really doing some weird stuff here, but it'll work out nicely in the end. So I'm letting y be in the set on the left. What does this mean? Well, that means y is in AX for all x in R. That's our definition of intersection. To be in the intersection of a bunch of sets, you have to be in every single set. Right, so for all index values, I'm in that set. Okay, but AX is this thing. So maybe now it's useful to substitute that in. It is y is in this open interval. no matter what x value I choose. And what does it mean to be in an open interval? Well, it means that you're bigger than the left endpoint and you're smaller than the right endpoint. So I could write down two inequalities. So y is bigger than the left endpoint, and y is smaller than the right endpoint. Right, this is why it's important to really think about this as an interval. I know we don't work with those much, but here's how it works. So, all right. Now, what do we want to do? Right, we have these two facts. Our end goal is to show that y is in 2, 5. It's to show it's in this interval from 2 to 5. To be in that interval, we would need, again, you could write out two inequalities. That means y is greater than 2 and y is less than 5. So that's where I want to get to. How on earth can I do that? Well, it's important to remember this claim up here held for all x values, right? So I could still say this holds for all real numbers x. And since it holds for all real numbers, what you can do is pick a particularly nice value of x. And I think I'll leave this as a question mark. Shouldn't be too hard to figure out, but you should be able to choose an x value so that this inequality becomes this inequality, and this inequality becomes this inequality. Hopefully you can see what that x value is without too much trouble. But I don't want to do all the work, so that's enough of a lead. And that will successfully show subset in this direction. For a subset in the other direction, we're going to want to let, again, I'll say y, or I suppose I could say z if you don't want to reuse the same letter. Doesn't really matter because they're two separate arguments. Right? I've split it into two cases, so I could use y if I wanted to, but maybe you guys are more comfortable doing this. Okay, what does this mean? Well, that means that z is greater than 2. Right, same exact story, sort of working backwards. Z is greater than 2 and z is less than 5. Okay, and now my goal is to show that this value of z is actually in the intersection of all these ax's. But that would mean z is in this open interval. For any choice of x I get. Which, okay, translating it again, would be like saying z is greater than this left endpoint. For any real number x, and z is less than the right endpoint for any real number x. So that's my goal. And this is certainly the trickier direction. Right? But the principle is sort of similar. I have an inequality here that I want to transform into an inequality here. I have an inequality here that I want to transform into this. Okay, so let's focus on that first inequality maybe. How on earth am I going to do that? Well, you might notice some nice properties of the absolute value function. So we know the absolute value of a number is always non-negative, first of all. So I could say, note that this absolute value is always greater than or equal to 0. Right? And so now I'm looking at this and thinking, okay, I have z greater than 2, x minus 1 greater than or equal to 0. And this inequality has sort of both of these terms mushed up together. So I'm going to want to try to take these two things and transform them into this inequality at the bottom. That's our entire goal. And so, well, the first thing I could do is I could just expand a little bit. Right? If I know something about the absolute value of x plus 1, what about negative absolute value of x plus 1? Well, you'll recall if I multiply by -1, the inequality sign flips. Okay, and then looking back down here, I could expand a little more. Because really, I want to think about 2 minus something. So that's sort of like, adding 2 on either side of this inequality. And if I were to do that, that would be 2 minus x plus 1 is less than or equal to 2. And now I'm looking at, okay, I want to get to here. And I do have an inequality involving exactly that expression. But how do I get the z involved? Well, looking back up here, we know that z is greater than 2. Another way to phrase that is 2 is less than z. And looky here, I have a 2. So I could just say right here, 2 is less than z. So tack that on. And what that gives me, if I just highlight the important bits, is it gives me that inequality. Right? So ignoring what's in the middle, these inequalities kind of chain together, and you can say 2 minus the absolute value of x plus 1 is less than z, which is exactly what you want. Here, it's just flipped around. So I can say, hence, maybe I will write it the other way around, z is greater than this. All right. Maybe that's enough, right? That gives us one equality. You would want to do something similar on this side. Say, note that something happens so that we get this second inequality, namely this one. Z is less than 5 minus x plus 1. Or that was supposed to be 5 plus. Congrats if you caught that. Anyway, I'm correcting it now. So we would like to get to here from a very similar line of logic. So you should be able to write that down. And therefore, in the end, what you get, we showed subset in both directions. So therefore, you do in fact get that the intersection of all these weird things, these wacky intervals, is in fact the interval from 2 to 5. All right, and that should help you with a similar problem in chapter 8. Let me know if it doesn't. Let me know if you want to see any of these details filled in. But in my opinion, math is something that you have to practice yourself to get good at. It does no good to just watch me do it all day long. But if you get stuck, let me know. All right, good luck.